right, welcome. So, just to introduce myself, my name is Oystein Kolsrud. I work at this company called Qlik, located in Lund in Sweden. Normally I'm a software developer, but I also, well, they're very generous to let me do things like this and talk about things that I think are fun. And today I'm going to talk about the Turing Machine. How many have heard about that before? All of you, excellent, yeah. How many has actually read his original article on it? There's one there, for real? Yeah, okay. So I was here at BuildStuff actually two years ago. I was talking about functional programming then. But during that conference, I was recommended a book on his article. The book is called Annotated Turing. I can highly recommend it. But this is basically, well, that was my main source of information when I made this presentation. Because I found it's a really, really interesting story surrounding that. I know we learned about this machine in university, we talked about it a little, but I definitely never heard about its historical context or what Turing was actually trying to achieve with it. So that's what this presentation is going to be about. It's more of a history lesson than anything else. Not much code in here, so if you want to see code, you should go to another room. Yeah. Anyway, so to understand what he was trying to achieve, we have to talk a little about this guy, David Hilbert. Have any of you heard about him before? A couple of guys, yeah. He's mostly famous for what is known as the Hilbert problems. It's a set of 23 mathematical problems that he envisioned would be something that mathematicians should work on, and that they are sort of the holy grail still, some of them, in mathematics. But he was a professor of mathematics at the University of Göttingen in Germany. It was a very prestigious university back then at the turn of the previous century. A lot of Nobel Prizes and everything from that pouch. And we're far ahead a long way ahead in the field of mathematics also. And he was one of the leading mathematicians at the time. And in Paris in the year 1900, there was this big mathematical conference in Paris where he was giving the honor of holding a keynote speech. And he did something quite bold, and that was that he focused this whole speech he had on talking about his philosophy of mathematics. And the ideas, well, the title here is in French, I'm not going to try to pronounce it, but it's basically titled something like Future Problems of Mathematics in English. And what he did was he tried to stipulate what he thought should be the main effort of the mathematical community of the coming 100 years. That's a pretty bold thing to do. And apart from that, he listed these problems that he thought were the focal point of, well, the main unsolved problems of mathematics of the day. And he envisioned that mathematicians would take this sort of as a competition and try to really do what they could to solve these remaining problems with mathematics. And they did. First problem was solved just a couple of months after his speech. Some of them are still not solved. And if you do, you will become very, very famous. They are pretty hard though, and people are working on them. But anyway, all of this boiled down to one of his main philosophies of mathematics, which was that mathematics are riddles. Mathematical problems are riddles that are there for us human beings to solve. And sort of the main task or purpose of a mathematician is to take these riddles and do whatever we can to make sure we solve them and thereby bring the total knowledge of the human race forward, basically. So he had a really interesting philosophy surrounding this. And also very important here, he thought that every mathematical problem can be solved if we just together as a society put our minds to it. Later on, this was called the Hilbert Program. Was one of the fundamental things here that because everything could be solved, he envisions that we could do this special quest in trying to find a very rigorous foundation for what mathematics actually is. And this Hilbert Program consists of three main topics. The first was to find a formalism. And a formalism would be a set of axioms and the rules of how to combine them and manipulate them. And the goal here was basically to find the smallest possible building blocks that we could base all mathematics on. So they were searching for these components that would be something like what we are doing today within particle physics, where we try to find the different elementary particles. So that was the first, devise a language and a set of rules for how to use that we can use to define mathematics once and for all. Second step was to have some form of completeness proof on this. So given this formalism, this language and the rules, we should be able to devise a proof that could show that every mathematical truth could be derived from this language. Because if we didn't, there would be some axiom missing or some rule missing. So this will be a sort of a goalpost that will say that, okay, now we have the language in place that can prove everything. And the last thing he wanted was a decidability. So given this language, that would be complete, that would cover everything, he wanted mathematicians to find an algorithm, a way to use this language so that we would know that from these truths we could derive any single mathematical statement. And if we had this, that would be a truly remarkable breakthrough in the intellect of human beings, basically, because theoretically we would be done with mathematics. We could just sit down and take any mathematical problem, just feed it to some sort of machine, and it could come out with an answer saying that, yes, this is true, or yes, this is false. And a lot of people were doing research into this, and one of the most notable works was this one, the PreSPEA Mathematica. It was devised as a big 3-volume work done by Whitehead and Bertrand Russell. Bertrand Russell became famous later on as a philosopher, very active in the peace movements, working against nuclear weapons and stuff. But he was also a logician and a mathematician. And he worked on this. And here they did this. They tried to define this formalism and the rules, and this base of mathematics that everything would be based on. And this they took more than 10 years for them to write this. And this is a small excerpt taken from Wikipedia, by the way. But it's the end of a proof that shows that 1 + 1 = 2. So very, very basic stuff they were doing here. And you can see here the language that they derived, all of these strange characters and stuff that were used for being able to express what they wanted to do with these axioms and these rules that they have put together. It also followed by this note that says that the above proposition is occasionally useful. Yeah. Okay, so this was a big work that was going on. And this was a big step forward in the part of the formalism, and also in the completeness part. They were doing a lot of work there. But the decision problem was still there. This was also something that people were trying to investigate and see if they could attack in different ways. And in 1928, David Hilbert, along with another mathematician, William Ackerman, published a book called Principles of Mathematical Logic. And in this, they spent quite some time exploring that problem. And they also devised algorithms for how to solve quite a few different families of problems. So they were making headway here. But they also added this part that says that the decision problem must be called the main problem of mathematical logic. It was actually in italic also in their texts, not just me. So this was an emphasis that they were doing. This is a very, very important thing, because if we have this, then we have done this huge step forward in our common knowledge, basically. Hilbert retires in 1930. He was 68 years old, and he holds this farewell speech in Königsberg, or Kaliningrad it's called today, titled Logic and the Knowledge of Nature. And he ends, again, he summarizes this philosophy I have about how we can solve everything together. And he ends the talk with this quote that has become quite famous. Wir müssen wissen, wir werden wissen, which means something like, we must know and we will know, which sort of underlines his thoughts on this. Now this is where things get interesting. Because the year after, this guy comes along. How many here know about Kurt Gödel? A couple of guys. Okay, excellent. Very, very special person. He's worth a talk in himself, but I'm only going to mention him shortly. He also became a good friend of Einstein later, by the way. But anyway, he was born in Austria-Hungary at the time, today the Czech Republic. And he published in 1931 a paper with this title, On Formally Undecidable Propositions of PreSPEA Mathematica and Related System 1. He was supposed to do a follow-up where he would sort of elaborate on what he did, but he never did so. Because in this paper, he published something that has later become known as Gödel's incompleteness theorem. And this, I would say, must be one of the most surprising results in mathematics. Because what he was able to show and prove was that when any given system, such as PreSPEA Mathematica, there will always be statements that can be expressed that are true but unprovable. And that was a disaster for Hilbert's philosophy, because he basically showed that what you're trying to do is not possible. And the basic foundation for doing all this work with PreSPEA Mathematica was gone. It was pointless. They could never achieve what they were trying to do. And when Hilbert heard about this, he said that he became pretty angry. But there's not much you can do, right? If you have a proof, you have a proof. There's no point arguing about it, unless you can find a problem in the proof, but you couldn't. So this was a very big breakthrough, and it turned mathematics on its head at the time. But could still be possible to not prove if something is true or not, but to devise an algorithm that would show whether or not something is provable. It's not the same thing as deciding if it's true or false, but deciding if we have a fair chance of actually getting there at all. And this is where Turing comes in. So Alan Turing, he was born in London in 1912. He went to Cambridge University. And in the spring of 1935, he read a course called Foundations of Mathematics. And one of the sort of highlights of that course was going through Gödel's incompleteness theorem. But they also covered this decidability problem. And there they express it like this. Is there a mechanical process which can be applied to a mathematical statement and which will come up with the answer as to whether it is provable? So a mechanical process. So then we need to think about what a mechanical process is. And this must have set his head spinning, because he started to think about what such a process could be, and what it could accomplish, and more importantly, what it could not accomplish. And that's where the Turing machine comes in. So, in April 1936, Turing delivers a draft of a paper called On Computable Numbers with an application to the Entscheidungs problem. Entscheidungs problem was another word for this decision problem. And in this, he describes a machine, which consists of 3 different parts. First of all, a finite state machine. Finite is important here. Second one is an infinite tape. So a tape that extends forever in both directions, but it's sort of one-dimensional. And finally, a head that can move along this tape and read and write symbols according to the state machine. And the purpose of this machine would be to produce computable numbers. I'm not going to talk much about what he means by computable here, but that's an interesting topic as well. So, now we go into what he actually does in his speech, or in his paper. Because the first thing he does is to start describing this type of state machines. So this is one of the state machines actually taken from his paper. And I'm going to explain a little what you're seeing here, but it's basically split into 2 different main columns. You have a configuration and you have a behavior. And the idea is that given a certain configuration, you will do a certain operation, and then you go to some form of next configuration or a next state. So basically a state machine. You always start up in the state B, B for begin, probably. He doesn't give much of an explanation of why he gives the names he does, but B is always the starting state. So what happens here is that we start here, start in this configuration with B, and the head is down here. Then there's no symbol under the head. So we print a 0. P stands for print 0, then move right. So a 0, then right. And then we go to the next state, C, which is over there. And now there's no symbol under here. Again, we just move right. We don't print anything. Then we go to E. Then we print a 1. And go right. And then finally we go to F. Move right there. Now we go back to B. So we basically do a loop here. And we continue like this forever. It writes 0s and 1s, 0s and 1s, 0s and 1s. So now we have a machine that prints all these digits. And to turn that into a number, we basically take these digits, put them after each other, and at a 0 point before. So this machine computes numbers in the range of 0 through 1. Anyone know what number this is? If you print it in, interpret it as digital? No? This is 1/3. That's 1/3 written digitally. So this is a machine that can compute the digits of 1/3. And as you know, that sequence will always repeat, right? Just like if you divide 1/3 in decimal numbers, you will get a 0 followed by an infinite number of 3s. In binary, you will get the infinite number of this sequence, 0, 1. Now this sequence also has a repeating sequence, as you can see. So it's quite easy to just write a table that simply prints those and go back and prints them all over again. But not all numbers are like that. Not all numbers have a repeatable sequence. Anyone know a number that does not? Pi, yes, excellent. First one that comes to mind. Square root of 2 is another one. So a lot of them actually, all irrational numbers are of that type. Rational numbers, like 1/3, can always be written as a repeatable sequence, but irrational cannot. So the interesting numbers are the ones that are irrational. And the next number he's going to write is this one. This is a pretty weird number, but I don't know if you can see the pattern here. Anyone want to take a stab at it? Yes? Yes, exactly. So for each cycle, if you want to call it that, there's one extra one. So you start with 0 ones, then 1 1, then 2 ones, and so on. So this obviously does not have a repeating pattern. We cannot just write a one big machine that will do this for us. We'll have to do something smarter. And this is a machine that does that. A little more complex, and I'll go through this also and what it does. But first of all, I'm going to talk about some simplifications it does. Because the original table was very simple in that there was just one operation here, or one print and one move, and one symbol, but here it does some simplifications. First of all, there can be multiple operations in each column. Secondly, there can be multiple characters or symbols here that the head can read in each column. But it's always, in this article, is very emphasizes very much that it's always possible to go from these simplified tables to the original table that has this very small set of operations for each line of the table, which becomes important later. So what does this table do? Well, again, we start off in state B, and this first state is some form of configuration or setup state, basically. So we write these symbols. I use this symbol here. In this article, he uses the letter called schwa. I think it's from Hebrew, but I'm not familiar with it, so this was much more readable to me. But it's basically a stop sign. He uses it as a stop sign. So from time to time, the head will just move back across the tape until it reaches one of these signs, and then it will do some operations. So I wrote these two symbols, 2 stop signs, a 0, another 0, and then it moves to left. So after we have done this, we will be at this state. So the second last digit that has been written. And after that, we go to O. So now we're being in the actual operations. So now we have to pattern match whatever is under the head with what is in this table. So it could be either a 1 or a 0. We have a 0 here, so it's this line we do. So we do nothing and just go to the next state, Q. The same thing here. We have to match on what's under the head. So as long as there's any symbol, we will be looping back to the same column or same row. And what we do is just we move 2 steps. And the result is that we will just be moving along these symbols as long as there is any symbol under the head. So we'll end up here, at which one point we print a 1, and then move left. So now we're there. Then we go to the next stage, P. So in P, again, we have to pattern match. There's no symbol under the head. So we just move 2 left, and go back to P. So we do that as long as there is no symbol, until we end up here at this stop sign. Now that means we have reached the start of what we have printed on the tape. So then we go right, and move to F. What happens here? Well, as long as there is a symbol, we move 2 right, and go back to F. So again, we will just trigger along these symbols until we reach the end of what we've written, at which point we'll print a 0, and move 2 left, and then go back to O, which was at the start here. So now we've done the first iteration, and written the first symbol here. So we are now written up to there. Now the interesting thing that happens in this table is the X's here, and I haven't seen that yet. In order to illustrate how that works, I'm going to skip one more full cycle into the computations. So now we're here. We always start at the second last digit in each cycle. So now we are here. There's a 1 under the head. This is the one that matches now. So what do we do then? We go right, 1 step, and print an X. And then we go 3 left. And then we go back to the same state. Same thing again. There's a 1 there, so we go to the right, print an X, 3 left. And what it has actually done now, and now it's done in this stage, so we go to Q, is that it has put an X next to every 1 in the previous turn of previous cycle of operations. And what it does now is that it will wind to the end. As long as there is a symbol, it will move to the end and write the 1 and move left. Then we go to P. So what happens now? Well, there's no symbol here, so we move 2 left. Now there's an X there. What it does now is that it erases it, E for erase. So it removes it, goes right, then it goes back to Q, which is over here. And what this does is it moves along the digits till it reaches the end and prints a 1. You see what it does? It basically goes back, picks up the x's, and moves them to the end as 1s. So next time we will go back here, pick up this one, and turn it into 1 at the end. And since we always start by writing a new one, there will always be 1 more for each turn of the cycle. So this is a table that is able to compute that. And he has basically divided it into these different states that have their clear responsibility. Now the next thing he does in his paper is to show, well, he does a couple of other tricks for simplification to make it easy for him to write. But he basically shows how to define a number of like convenient tools, like a way to tag a certain sequence of characters, or a way to compare 2 different sequences with each other, or a way to take one sequence and copy it to somewhere else, and do all these type of operations just by writing these types of tables. But it's always keen to show that it's possible to go back to this original format. In fact, he shows that it's possible to write every line of such a table in just 3 different forms. And these forms are identical, except for this operation which concerns moving. So this one moves right, left, and N for neutral, doesn't move at all. And by having these 3 lines, you can express any table that you want. So what I've done here also is just remove the naming, or made a new naming convention. So instead of using A, B, C and such, you can just use an indexed Q. So state B would be Q0, for instance, and then so on. And for symbols, you don't actually need the symbols either. You can just use a symbol for a symbol, basically. You don't care what the symbol is. You can just you do the same thing there and index it. So if we use this method to express our first table, the one where we printed 0s and 1s, it will look something like this. So first state is Q0. We now give a special meaning to 3 of these symbols. So S0 is 0, S1 is 1, and S2 is blank. Now we can pattern match on S2, which is the blank. If that's the case, we print S0, which is 0. And then we use those symbols instead. So why does he want to do this? Well, he wants to have a uniform way of taking any such table and being able to print it out in one long line. Because now that we have this format, we can take this line, just concatenate them, and do like this. So it's basically a serialization of each table. So it takes a semicolon and just concatenates each sequence like this. Now he does some more massaging, basically, of the type, or the way he writes these tables, because there's some simplifications we can do. First of all, the P is no longer needed, because it's always between 2 S's, so we can just remove that one. And next step is these digits. Instead of using a digit as an index like this, he replaces the digits with just a sequence of characters. So instead of 0, we will replace that by 0 A's. Instead of 2, we will replace it by 2 A's. And if we do that, we end up with this type of sequence. And this is called the standard description. He uses this as the way to give a standard way of describing any table using these characters. So why would we want to do this? Why do we want to write something down like this? Any ideas? What's that? It's a program, basically, yeah. So what he wants to do is to write this down on the tape. Like this. Because if we do that, then we can construct a Turing machine that can analyze these instructions and execute them. And this is what he calls the universal machine. And that is basically Turing inventing the programmable computer. Have any of you seen there was a movie coming out about Turing a couple of years ago called Imitation Game. Any seen it? Yeah, a lot of you, good. So there's a scene there where the female main character comes up to him and says, wow, you invented the universal machine, or you built the universal machine. And this is what she's talking about. But the interesting thing here is that this was not the goal of what he was trying to do. This was just sort of a side effect. A side effect of trying to solve this problem is to produce the program on a computer. Interesting thing. Also, he never had actually any thoughts on building this. This was just a thought experiment. So he had no intention or ambition to actually go ahead and build this machine. Because he was on to something else. And he was not done with this yet, because we're going to do some more massaging of this description. So this is now called the standard description. We have this sequence of characters here. And one thing we can see is that it consists of a surprisingly few characters. In fact, it's just 7 characters. These 7 here. Q, S, A, R, L, N, and semicolon. Now what we're going to do is we're going to replace these characters by numbers. Instead of Q, we write the 1. Instead of S, we write the 2, and so on. And if we do that, we end up with this description. And this is now called a description number. So why would we want to do that? What's that?
Encode as bits.
Encode as bits? Yeah, that's one possibility. What's so special about numbers? Why do you want a number? Well, there are actually 2 aspects of numbers that are very, very special to numbers. The first thing is that we can count them. And the second thing is that there are infinitely many of them. What he has basically done is he has shown that Turing machines are enumerable. We can start counting 1, 2, 3, 4, 5, 6, 7, 8, and eventually we'll hit some form of Turing machine, or a number that could be interpreted as a Turing machine. Not only that, but since he has shown that any Turing machine can be written like this, if we just count long enough, we will reach any possible Turing machine that exists, or that can exist. Everybody agree on that? Excellent. So if I just write longer, this is a pretty big number. I have no idea how many characters that actually are, but somewhere in there we will find these gold nuggets that will be actually do machines that do interesting things. So this one produces zeros and ones, but we could find something that produces the digits of pi, for instance, as well. So now we're approaching what is actually the proof that he wants to do in his article. And before I do that, I'm going to introduce these 2 terms. Circular and circle-free machines. And there are basically 2 conditions for when a machine is considered circular. And the first is that a machine is circular if it reaches or can reach an undefined configuration. So basically a crash. You reach a state that has not been defined. And this is an example of one of those. So we start off in B. There's no symbol here. We print a 0. We do not move. Then we go back to B. So now we're here again. We want to pattern match 0. There's no state for 0, so it crashes. We don't know what's going to happen next. That's one state. If it crashes, it's circular. Second thing is that a machine is circular if it ends up in a state where it no longer produces any zeros and ones. Basically, it's hanging. And this is an example of that. We start off in B. There's no symbol there, so you move right and then go back to B. But we never print anything, right? So we'll just be moving rightwards across the tape without doing anything. So that's a circular machine as well. So it either crashes or it hangs. And if it's not circular, then it's called circle-free. So now we're going to build a very special machine that we will call Age. Yeah. I've tried to figure out a better name for it when I did this presentation, but I couldn't come up with one. And Turing calls it Age because it comes after G in the alphabet. Because yeah, machine form was G. It wasn't too good at coming up with names either. Anyway, we're going to build a machine Age that performs like this. First, we're going to assume that we have 3 Turing machines, circle-free Turing machines that operates correctly, without crashing and without hanging. And they do like this. First one is correct. Is correct is a machine that takes a number and checks if that number is a correct description number. That one is quite easy to implement. For instance, you can filter away everything that includes a 9, for instance, or a 0, because those are not part of those. But it's sort of a program exercise that we can all do, I assume. Next, we want a machine that we call print digit. And this machine takes a description number, which represents a correct Turing machine, and executes that machine. So basically, we will need the universal machine that he has already shown can be built. And given that, after executing it, it will pick out the nth digit from the machine. So if we, for instance, you run print digit on the 1/3 computing machine and says that we want the second digit, well, then we'll take 0, 1, and take 1. That will be the result. And finally, we want a machine that we call is circle free, which basically takes a description number and decides whether or not that machine is circle free, that it doesn't crash, it doesn't hang. So now we're going to build a machine H that performs like this. Well, we start counting 1, 2, 3, 4, 5, 6, and so on. And eventually, we will reach our first correct description number. We will check if it's circle free. If it is, then we'll print the first digit of that machine. If it's not, then we'll just continue. So it will print the first digit from the first circle-free machine, the second digit from the second circle-free machine, and so on. And if we write this in pseudocode, it would look something like this. So we start off with these two variables, a description number and an n, which is the nth we're going to take. And then we just do an infinite loop. So if the description number is the correct one, and it is circular-free, then we print the nth digit of that machine, increment n, and for each loop we will increment the description number. And then we start running it. And 1, 2, 3, we start counting. And eventually we will hit the first circle-free machine, which is this one. And this is a machine that prints a 0 on every single square. Second machine we will hit is this one. Prints the second digit from that. And this is one that prints a 1 on every single square. So the first digit or the 0th digit of this machine will be 0, first will be 1, and so on. We will continue. And then we'll keep counting. 2, 3, 4, 5, 6, 7, 8. And eventually we will hit a very, very special number. Anyone want to take a stab at it? Yes, good. Because this machine can also be interpreted as a Turing machine. Which means that if we just count long enough, we will reach a number that represents this machine. Well, then what's going to happen? What will it print for itself? Well, we will have to analyze it. So first of all, is it correct? Yes, of course it's correct. Otherwise it wouldn't be the machine that we are running here. We don't write any bugs. Is it circle-free? Well, unclear, but let's say it's not. What happens then? Well, then we just continue. And then we'll go into the next loop and we'll eventually hit some other machine. And it will start writing digits from that one. But since it's always possible for it to write a new digit, it must be circle-free. So this must be true for this description number. So what happens then? Is correct? Yes, it is. It is circular. So now we're going to print the nth digit of H itself. Now let's say the machine that the H is the 10th circle-free machine to define. It's probably more like 100 billionth or something. But let's say it's just the 10th. What's going to happen here when it tries to print its own digit? Well, what this function does is that it executes the machine and tries to pick the nth digit. So what's going to happen? Well, I want to produce the 10th number. Okay, so we start over again. And we print the first, the second, the third, and so on till we reach the 10th. What happens there? Well, same thing. We end up here. And it starts over. The first, second, third. And it's never going to print anything. It will never complete. But that's not possible because we already said it's circle-free. So what happened here? Anyone? What's that? It's a paradox, exactly. It can't both be circular and circle-free, right? So what's wrong? The universe. Oh no. Yeah, exactly. Well, since we have reached a paradox, we must have made a wrong assumption somewhere. And the assumption we made is that it was possible to write this function. This one is simple to write. This one is, well, it's not trivial to write, but as long as you have the universal machine, it's not impossible. We just assumed that we could do this, but we can't. He has proved that it's impossible to write a function that takes a description number and determines if it's circle-free or not. This is basically a proof by contradiction. You do an assumption and see if it leads to something that contradicts itself. If it does, then the assumption was wrong. It can print neither 0 or 1 for itself. Now in computer science, you often, have you heard about the halting problem?
The what?
The halting problem?
Yes,
No?
you can't prove termination.
Exactly. Exactly the same problem. It is not possible to write a computer program that takes any other program as input and determines if that program will eventually stop or not. You can't do it. You can try if you like, but you're not going to get there. Now remember the Entscheidungs problem, the decision problem? Is there a mechanical process which can be applied to a mathematical statement and which will come up with the answer as to whether it is provable? Now the next part of Turing's paper is dedicated to this. And he shows that for that algorithm to exist, this is-circle-free method must exist as well. So it follows from that the answer is no. There exists no such algorithm, no such mechanical process that can be used. And there is the answer to the mathematical problem that he was working on. Unfortunately, there was someone else who was working on the same thing. So there was a guy named Alonzo Church. Anyone heard of him before? Yeah, a couple of you. Yeah, he developed something called lambda calculus, which is the foundation of functional languages, basically. But he published a paper titled "On an Unsolvable Problem of Elementary Number Theory," 36, which touched on this very similar things that Turing was doing, in a very, very different way, though. But he also submitted this note, a note on the Entscheidungs problem, on April 15th. Turing submitted this paper on May 28th, so he was 6 weeks late. Ouch, yeah. His supervisor, Turing's supervisor, when he noticed this, he wrote a letter to the paper and said that, hey, I have a student here who's going to be totally devastated by this. But I hope you have the heart to publish it anyway, because the way he did it was very, very original, and I think it's worth taking that into account. And they did. He was allowed to publish, but he had to add an appendix where he proved that the results that he had gotten to were equivalent to what Alonzo Church got. So we added that, and he was able to publish the paper. But in the end, what is remembered for is not actually solving this problem, because, well, science is very harsh in that way. If you're scooped, you're scooped. You don't get any credit. But obviously, the way he did it is something that has become legendary in many respects. After this, actually, he went to study under Alonzo Church. So he took his PhD under him, because they said, hey, you're working in the same topic here. You should work together. You can do miracles if you do. So he went to Princeton University in the US. I studied under him. And what about Hilbert? Well, Hilbert had worse problems to think about. He was still in Germany at the time. Hitler came to power, 1933. And under the Nazis, Jews were not allowed to teach in universities. And the University of Göttingen was pretty much devastated about this. And he was, at one point in 1934, the year after Hitler came to power, he was at a dinner and sat next to the German Minister of Education. And he got the question that, how is mathematics at Göttingen now that you are free of the Jews? And the answer was basically that mathematics at Göttingen, there's no such thing anymore. Hilbert himself came also under suspicion of being a Jew. Yeah, suspicion of being a Jew. And basically, from what it says from his name, is a very traditional Jewish name. And he was sort of pushed out into the periphery as well. And he dies in 1943. He was 81 years old at the time. And he's buried in Göttingen. And this is actually his tombstone in Göttingen. And down at the base here, you can't see it at the this projection, but down at the base is this quote from him: "Wir müssen wissen, wir werden wissen." Thank you. Any questions? Yes?
More like a tiny comment. You mentioned the letter that Turing used was
Yeah.
called schwa or something like that.
Schwa, I think, yeah.
That is not a Hebrew character.
It is not,
I
okay.
don't know what it is, but it's definitely not.
Okay, yeah, all right. I don't know it anyway, so. Yeah. Anyone else? Yeah. So during the war, Turing became involved in the code breaking, right? That's what everybody knows about him. In popular history, popular science, that's usually what you hear. But after the war, he was also heavily involved in building the first computer. And the first computer was built called ACE, Automatic Computing Engine, or something like that. And it executed its first program in 1950. And Turing was the one doing the programming. So in reality, Turing became the world's first computer programmer at that point. Yeah? Yes?
That I take issue with, because depending on how you define a computer, take back about 130
Yeah,
years.
Ada Lovelace. Yes.
The analytical engine, which was ironically not proven to work until about 100 years later.
That is true. Actually, Charles Babbage, what he was doing was something in the same direction. I don't know if he did any theoretical thinking about it, but he actually tried to build it.
He designed it, and it
Yeah.
didn't work eventually.
Yeah. Too complex to get the mechanics in order, I think. Yeah. Yes?
I want to get your opinion. Well, some mathematical problems are now being proved by computers, like so-called dirty proofs. What do you think of them?
Well, I'm not a mathematician myself, so I don't know if I have a very strong opinion on that. But I mean, for some problems, what you can do is basically brute force it. Since you have such an extreme computing power, there are some problems that you can actually, well, let's try all combination and see what happens. Yeah. There's some tricky parts to that, though, because it's very hard to verify the proof afterwards. You have to verify the program itself, not the proof, which adds a different level of well, skill sets needed for a programmer. But I mean, if you try every possible combination and you find that it's true for all combinations, then yeah, it's a proof, I guess. Any other questions? Also, there are a lot of problems that can be solved with computers. That was one of the things that David Hilbert was investigating, right? He did find algorithms for proving a large subset of problems or families of problems. So not all problems are impossible to deal with by a computer for real. Which is also interesting. Yes?
But does it mean like that you cannot know if the problem is actually unsolvable because of his proof sometimes?
Yes.
So you don't know?
No? That's true. So you might be working on something that is impossible to solve.
And you
That's
never
true. No? You can have a hunch, I guess, about where it's leading and such. But one of those that were sort of in that potential category was this Fermat's last theorem. I don't know if you're familiar with that. It's also a very, yes?
If you want a more accessible example, the FOP proof for distributed systems, in that it's impossible to build a perfect detector, fault detector on an asynchronous network.
Yeah.
Just having that proof that it's impossible to do that meant that a whole generation of scientists could stop
Oh, yeah.
focusing on the
Oh,
wrong
yeah.
things that are inherently intrinsically.
So proving that something is impossible is, of course, a very big thing to do, because you know that there's no point in us doing this, like PreSPEA Mathematica. If they had known up front that what they were trying to do was impossible, they probably wouldn't have spent 10 years trying to do it, I would guess. I'm a little unfair there, because that work was actually useful in many other aspects, and there was a lot of other research done from that. So, but still, the fundamental thing they were trying to do was impossible.